So I wrote this in the very back blackboard. I'm not going to erase it. So don't worry too much about copying this out. This is things that you probably all know very well. But maybe you have seen it in a slightly different context. But you can then copy it out at the end. And let me just remind you, this very simple example, let's work it out a bit more explicitly about the free massive scalar. So the claim was that the free massive scalar, if the mass is very, very large, or if the distances are very, very long, we don't care about the mass and we end up with nothing. If on the other hand, we are at very, very short distances, that is, we excite very high energies, then the mass is irrelevant, then we have basically a free massless field, and this was the cartoon. And of course, we can see this very, very explicitly. If you just compute, say, the propagator between two scalar fields. Let me remind you what it is. So in momentum space, it's trivial. It's p squared plus m squared, right? Then you have to Fourier transform it to go to position space to see how it looks like in position space. Of course, as soon as you have momentum space, you don't need to do anything else. Then you know immediately that if p is very large, you can ignore the mass, and then you are done. You see immediately that it's massless. But okay, let's still do it in position space to get some intuition. Okay, very good. So 1 over p squared plus m squared. There is a nice trick. You can write it as an integral of e to the minus t times p squared plus m squared. Now it's in the exponent. It's okay? Again, you integrate from 0 to infinity. Now, because it's in the exponent, you can complete the square, and you will get rid of this d-dimensional integration because this is just Gaussian. When completing the square, you add this term x squared over 4t. Okay? Is it clear so far? Now, x squared, remember, this is just the distance between 2 points. Indeed, it only depends on the distance between 2 points. So here I already replaced this x squared by r squared. So at the end, we did the Gaussian integrations. We just got a bunch of pi, some t, and then we are done. We are left with this integral here that we can compute. If you just plug it in mathematics, it's a Bessel function. Now we can see how this Bessel function behaves. And you can conclude that this Bessel function behaves as e to the minus m times r if this quantity is very large, or as a power like if this quantity is very small. So for r much smaller than m, it behaves as a power. If the distances are very large, it disappears. It decays exponentially. And one nice way to understand it is that a mass very large is kind of a classical computation. You just have a classical particle propagating. And indeed, you can see that if the mass is very large, you can just do a saddle point computation here. You fix t, and then t star at a saddle point is something like r over 2m. And then you just replace it in the exponential, and you get an exponential decay. Another way of thinking about this is that a field theory, you can describe a propagation of a scalar as a sum over paths of particles from point x to y averaged by e to the minus the length of that path times the mass. So if the mass is very large, only the straight line contributes, and you get e to the minus mass times length. And yet another way to think about it is that you are doing a very large integral, an integral where this phase is very large, so what contributes is the first pole, so when p is equal to m, and then it will again lead to this exponential decay. Okay, just technical arguments to say the same thing that we knew very well physically, that if you have a particle with mass, the correlations decay very fast. If the mass is very small, if the if the distances are much smaller, 1 over the mass. 1 over mass. If the distances, on the other hand, are very small, we can basically ignore the mass, and then we just get an integral. We rescale t out, and it just gives us some power times some number. And then we immediately get the power law behavior. So, okay, so we see very well. We have a free scalar field here in the UV, and we go to nothing in the IR. Okay? Of course, we can have slightly, but I mean, even though still very simple, we can have slightly more interesting examples. We could imagine, for example, three free fields. But let's imagine we have one field, d phi 1, with a big mass, a phi 2 with a small mass, and the massless phi 3. And what would happen? Well, we would start in the UV with 3 massless fields, because the mass, if you are at really, really very high energy, 3 massless scalar fields. And then in the infrared, what will we get? If we zoom out? Sorry? 1 massless scalar field. Only phi 3 survives. So in the IR, we get one massless field. But of course, here we could, I mean, maybe it is nice here to add something interesting. That of course, at some point, if, for example, there is a region where this M1 is much bigger than the energies which we are considering, which are much bigger than this M2, then in practice, here, we are passing by very close, not exactly, but we are very close to a CFT, which has two massless scalars in this region. That is, the correlation function between the fields phi 1 decays exponentially, but the correlation function between phi 2 fields and between phi 3 fields behave as a power. Okay? So we are in a regime where we can ignore the mass, we can ignore one of the masses. Yeah, where one of the masses is decoupled, but you are still at very high energies compared to the second one, and we are close to a CFT. And in general, what can happen is, so this is a very simple case where everything is free and there is no non-trivial RG. But in general, what you can imagine is that, for example, you would like to end on some fixed point, like this one here that we almost did, and you have to tune your parameters, like your temperature in the lab, such that as you are changing your parameters, you almost hit, you go away. Then if you tune too much, you hit and go away somewhere else. But if you tune it just right, you hit it there. For example, suppose you have a lambda phi to the 4 theory, like a critical theory to describe some kind of Ising model or some model with a Z2 order parameter. Then you have some lambda phi to the 4, but dynamically, by quantum effects, you generate a mass, right? So it's not up to you to say the mass is 0. But you start renormalizing and seeing how your Lagrangian is becoming as you integrate shells of high momentum. You start generating terms, and you might generate a mass. Then you have to tune your lambda parameter. You have to tune your parameter, lambda, which is directly related to the temperature in the lab, such that that mass is tuned to 0. And in that way, you would end up with a non-trivial CFT. So in general, we can have, say, some UV theory that can flow to some IR theory. Some other UV theory, very close by, just slightly different, can flow to another IR. And we have to tune if we want to go to the right IR. And the same IR can flow, can have, and will have different UVs. This is the kind of picture that we have some potentially many theories in the UV. We have potentially to tune our parameters to go to a particular fixed point. And there is some notion, some important notion of universality of the RG flows. There are fixed points of the RG flows, some basins of attraction where things go. So this is, if you want, a modern picture of how we think about quantum field theory. And this was one of the main motivations for studying conformal field theories. The other one that we did not dwell into much so far was ADS-CFT. The third one was string theory. And what I said we would do next is understand yet another motivation, which is that if we try, so we try to add, so let's see how to write. So let's see, if we try to add more symmetry to what we already have, that is to the usual Poincare, but not too much. By not too much, I mean if we add too much, as we will see, we will end up with two trivial theories. They have too much theory, too much symmetry, but they are too trivial, they are free. There is not free theory, so we don't want to start describing only free theories. But not too much, then this leads naturally to the notion of CFTs, supersymmetry, and integrable models. So, and this is where I want to start today. Okay. Any questions so far? So please stop me if I try to erase this. I will try to not to erase. Any question? Okay, so let's start with something very simple. But I think it illustrates already pretty much the physics of how dangerous it is, what can typically happen if we add too much symmetry, and why am I saying that adding too much symmetry naturally tends to lead to immediately a free theory. So to understand what's going on, let's consider the simplest possible thing we can consider, which is just non-relativistic particles described by usual quantum mechanics. Okay, so we just do quantum mechanics, non-relativistic quantum mechanics. Okay. And what I want to do is consider a wave packet. So I consider a wave packet, so some particle that is moving, and of course there is some uncertainty about its position, so it's some wave packet. That is, we have some wave function. That is, there is some momentum that is roughly P naught. It's centered around P naught plus I P x minus I P square over 2m t. Okay, that's some wave packet, which has some momentum p, and that's the wave function. Is it clear? Some preparated in a region where the potential is irrelevant, so it's just a plane wave, and we can give it any moment and integrate with a Gaussian to have some more or less definite momenta p naught. Now, if we ask, where is the particle? So if I write this wave vector, where is it? Where do I have a chance of finding this particle? Well, where the phase is not changing much. Right? So we ask, where is the phase not changing much at p equal to this value, p naught? Okay, and what we get, if we impose that this is equal to 0, is we just take derivative and we'll get something trivial. We get that x minus x naught plus or minus p over m t minus t naught. Okay, and it's at p equal to p naught, so p naught. So nothing special. We just the particle travels with some velocity. So it starts at some position x naught and travels with velocity p over m and some time t minus t0. Yes, just the movement of a particle. And then we try to see what happens to this description as we act on this wave function with symmetries. For example, with translations in time or translations in space. So let's see what happens to this wave function when we act on it with some symmetry, e to the beta times some charge. So this is some charge which is associated to some symmetry. And let this charge Qn be, for example, some p to the n. Such that when n is equal to 1, we just have momentum. When n equals to 2, we get energy. Okay? So from n equal to 1, this is just momenta. N equal to 2, this is energy. So this is familiar. And n bigger or equal than 3, these are new local charges, which are called higher charges. Of course, these are the most interesting ones. We want to understand what would happen if we try to add this kind of symmetries. But let's first focus on, let's first re-derive what we know should happen when we act with a momentum or an energy, with a momentum or the energy generators. So what happens is that in momentum space, these generators are trivial. They just shift the phase. So this just means that the phase becomes phase plus I beta p to the n. And therefore, let me write this in blue. Can you see well that this is blue? And therefore, what will happen here is that you will add here some term plus n beta p naught to the n minus 1. Okay? Very good. So now we see what this effect is doing. So if n is equal to 1, this is just equivalent to shifting x naught. Right? So if n is equal to 1, it's a quantity that is independent of p naught. It's just, I can just absorb it in shifting x naught. If n is equal to 2, this is just equivalent to shifting t naught. Is it clear? Is it what we expect? Of course. So what we are saying is that momentum generates translations in space. It tells you that the wave packet can be moved in space. And energy generates translations in time. Okay? Not surprised. Now, what's interesting is what happens when n is bigger or equal than 3. Then we see that we shift our wave packet. So our original wave packet is shifted but this quantity here that it's shifted, it's a momentum dependent shift. So we shift our wave packet by an amount that depends on its momentum. So what would happen? What would a theory that has this kind of higher symmetries, how would it look like? Let's suppose we prepare 3 wave packets and they are aligned to scatter, say all of them, and they are aligned to scatter in some region of spacetime. So this is what we do. Now, what does it mean to have a symmetry in your theory? It means that the amplitude for the probability amplitude for this process to happen is equal to the same if you act with one of these higher charges on it. This is the definition of a symmetry. And of course, I could add with plus or with beta. I can translate in positive direction or negative direction. But now what happens here? What happens here is that I shift these wave packets. But now I shift these wave packets here by an amount that depends on the momenta of the wave packet. So the different wave packets have different momenta, and I'm shifting them in different directions by different amounts. So what I conclude is that this picture, for example, if I shift these wave packets, I could end up with something like this, where instead of scattering now at the same position, I shift them, and now they scatter in pairs. And if I would do it in the opposite direction, with opposite sign, I could end up with something where I scatter in pairs, but in a different order. Now, of course, here something is implicit and very important, I should have said, of course. We are doing one-dimensional, it's really the simplest thing we could do. We are doing one-dimensional, non-relativistic quantum mechanics. Just there is a line, there is x. And then we conclude that there is something very interesting, that an S matrix, a scattering process where 3 particles are scattered to 3 particles, becomes decomposed and given uniquely by S matrices where 2 particles scatter with 2 particles, so 2 to 2 process. Okay? Is it clear? Yes.
So these qualities are absolute. Are they exact qualities? Or
They are exact equalities. A priori, you could ask whether they hold up to a phase, or only the probability could hold, right? You are thinking that the probability could work. If it would be, it could be just a phase. But still, it will tell you that the S matrix, maybe up to a phase, would factorize into 2-body S matrix. So this tells you already that this theory, the have higher charges, they are very special. What happens in these quantum mechanical theories is that all we need, so these are theories. So let's see, where should I write? So we end up with a 1 plus 1 dimensional theory. Whose dynamics is totally specified by giving the S matrix of two particles scattering with two particles that depends on the momenta of the two excitations, and by knowing what's the energy of a single excitation, which in this case is just p squared, and that defines all the scattering. That describes all the dynamics. Particles, when they scatter in a factorized way. And all we need to know is the two-body S matrix and the dispersion relation. These are very special theories. You see, it's the next to simplest theory after free theories. And these are what are called integrable theories. So these are the next to simplest theories. If you want to study a theory that is not free, this S matrix can be very non-trivial, this 2 to 2 S matrix. But any scattering process with many, many particles, you can always decompose into a sequence of two-body S matrices. So these are important theories. So these are integrable theories. Because of this huge simplification that all you need is this data, this infinite volume data, they are often exactly solvable, and a great deal is known about them. Okay? Now, this was in one dimension, or 1 plus 1 dimension. What about higher dimensions? What if we tried, so this, you see, we arrive, by trying to add more symmetry, we arrive at this notion of integrable models here, of two-dimensional integrable models. But what happens if we try to repeat this exercise in higher dimensions? Well, everything goes through. You just add some vectors in some places and so on, some indices and so on. But what will happen clearly with the physics is that now you can have some symmetries, if you have higher powers of momenta, that shift wave packets by amounts that depend on their momenta. But now if two wave packets were about to scatter, by shifting them, you can make them not scatter. Right? Because you can shift wave packets by amount that they depend on their momenta. If they are in the plane, they have to scatter sooner or later, and you always decompose it into a sequence of scattering. But in higher dimension, what you conclude is that the amplitude for a process where they were going to scatter is related to a process where they just don't meet at all. Something like this. Where this distance, this impact parameter, can be very large. So the S matrix, if we start adding too much symmetry, is just 1, and we get a free theory. So we try to add too much symmetry, we are dead. The theory is free. Okay? Now, let's try to think how we could evade this no-go theorem. How could we try to bypass? Is this the end? Is Poincaré all we can have, or can we still add some? So, of course, first of all, I was doing here a simplification. I was doing non-relativistic quantum mechanics to illustrate a bit of physics, right? But of course, you can trust me, there is such thing known as the Coleman-Mandula theorem, which is the rigorous way of doing more or less what I have done here. So this is, if you want, the cartoonish way of Coleman-Mandula, which tells you indeed that if you try to add more charges to a theory that has Poincaré, you typically end up with a massive theory, with a free theory. So how could we try to evade this? Well, one thing we could do is consider symmetries that are not bosonic, like fermionic symmetries, symmetries that will act in a very different way and don't have this sharp geometrical meaning immediately, at least, with respect to this kind of bosonic symmetries. And if you want, this is one big motivation for introducing supersymmetry. Supersymmetry are exactly this kind of fermionic symmetries for which this argument does not immediately imply that a theory is free. You cannot do whatever you want. You must still be careful not to end up with a free theory. But supersymmetry falls in the category of symmetries that are not immediately ruled out by Coleman-Mandula. Why is conformal field theory also in this list? Because you see that this argument depends very strongly on the notion of when you prepare a wave packet in minus infinity, very separated apart, it really doesn't know about the other guys. So this is true if your theory is massive. So if your theory have a mass, it's possible to separate things a lot, and things are very well separated. As soon as you don't have a mass, I mean, you have scale invariance. Who tells you what is far away or what is close? It's impossible in practice to define, to apply this argument strictly speaking, because the particles are never very separated apart in a conformal theory. When we say it's very large, but if there is no scale, it's very large compared to what? In other words, what happens in CFTs is that the S matrix, if you have massless particles, is infrared divergent. And okay, we are basing our argument on some quantity that we need to treat with lots of care. So strictly speaking, it would not apply. So unless, so this gives a free theory, unless we are dealing with zero mass. And this leads naturally to the notion of conformal field theory. Okay? Okay. Any question? Okay, so there was a question? Yes.
So would you mind explaining how you go from so that 3-3 scattering? How do you go from the 3-3 scattering to this scattering?
What was the question?
Would you mind explaining how you go from the 3-3 scattering to the 2-2 scattering?
The argument there was that you have three wave packets. Imagine you have here three lines that are about to meet at the same point. And now you shift these lines, you shift these three lines, but you shift them not by the same amount. If you shift them all by the same amount, of course, they still meet at the same point. Right? If three particles are meeting at the same point, if I do the same experiment tomorrow or if I do it there, of course, they still meet at the same point. But if I shift this one to the left and this one to the right and keep this one not moving, then I immediately don't scatter them. Or if I shift two of them and then the other one in another direction, then what happens is, so if I have something like this, and then I start shifting and I shift this one to this direction, then what I get is this, right? So if I shift this line, I end up with this. Right? So if I shift this line in this direction and this line is in, say, this direction, then I will end up with some picture like this. So if I shift the lines by an amount that depends on their momenta, typically what will happen is that I will end up with some picture where they no longer scatter at the same position. Scattering at the same position requires fine-tuning. If I can now shift them by amounts that depend on their momenta, this is the generic situation. Now, this is in one dimension, where if I can shift, but I always stay in the plane. So I can still have something very interesting, because they still need to scatter. But all I need to know is how two particles scatter. So I don't go, even though I'd never have three particles scattering, I still have scattering. This is still interesting. But if I am in higher dimensions, by this argument that I can shift the lines by different amounts, I can just make them very far away and not scatter at all, if I have the freedom to go outside the plane of the blur. And then that would lead me to a conclusion that the particles do not scatter at all, and then the S matrix is 1. Unless, even when they are separated in practice, they are not, because the interactions are long-ranged. And then I have to be more careful, and therefore, that could be the case for conformal field theory.
Sorry, so I don't understand why you say this is one dimension. It seems like it's the plane.
Well, I'm alternating, I apologize. I'm alternating between 1 and 1 plus 1, yeah. I say one dimension of space. There is one space, one time.
Yeah, so this doesn't this look like a
No, this is space. This is time.
Okay.
So they live in the plane and they move in time. This is an S matrix. So the bottom is incoming, the top is outgoing.
What happens if you have 4 particles scattering?
4 particle scattering, you can show that, I mean, what will happen is that you will also factorize into a sequence of 2 body scattering.
So you're claiming that you have another integral function, which is Q4.
But even Q3 would be enough. If you just act with Q3, it would be enough to delocalize completely the 4 particles. So if you have 4 particles scattering all at the same position, this will now go to, I don't know. Something like this. So they would now, they will now meet 6 times.
But you have now 8-dimensional phase space, so you should need 4 concept quantities.
I mean, you can see that typically, if you move these lines by an amount that depends on their momenta, this is where you typically go. Because they have different momenta, these 2 guys, so they will be moved by a different amount. So it's not like with one charge, you lift partially the degeneracy and then you need another one. No, it's just with a single charge, because it moves with these 4 lines with 4 amounts, immediately you go here. But what typically happens is that as soon as you have Q3, you have infinitely many Qs. That's typically what happens. Okay, very good. So now we can define what a CFT is. Now that we already discussed it so much and so on, now we can finally say what's the definition of a conformal field. Very good. So now we start with so we can define conformal field theory by imposing that the theory has this while invariance, this local scale invariance. So what does it mean? So our theory is uniquely specified by a generating function from which we can extract correlation functions. So we have some generating function of our theory in some space given by some metric G mu nu. And there is some current J, from which if we take functional derivatives with respect to J, we extract correlation functions. So these are sources, physically. So this, we have some integral over some fields. If we have a path integral, if we don't, I still have the left-hand side. But if we have a path integral, what is this object? It's some integral over fields, e to the minus some action that depends on this fixed metric, G mu nu, and this dynamical field phi. And then there is some integral that couples the current with some operators O of x. Such that by taking functional derivatives with respect to J and setting J to 0, I get correlation functions of my field O of x. And now for O of x, if there are several O of x, you add several such currents. And now I will write here some jargon that at this point you cannot yet understand. Okay? So to define a CFT, I need to define some notions such as primary operators and so on. So I'm going to write it still. But don't worry, we are going to understand very well what these terms mean. So here I'm considering scalar theories, and then this would be a scalar primary. I still want to write it even though it's not totally clear. Operator. For now, ignore the words primary. So it's a scalar operator with dimension delta. So delta is the dimension of the operator. In the same way that the scalars at dimension d minus 2, the exponent was d minus 2, or d minus 2 over 2. The d minus 2 over 2, sorry. This O has dimension delta. So it's an operator with dimension delta. So it means that under dilatations, it transforms with a power of by how much you dilate, to some power delta. It tells you how much, what's its dimension. How does it react to dilatations? Okay. So we start with some Euclidean CF quantum. This is an Euclidean quantum field theory. Right? what else do I want to say? I want to say that, of course, correlation functions of operator you extract by doing derivative with respect to j at point x1 with 1 over square root of the metric at point x1, and then a bunch of other derivatives if you have more fields acting on e to the minus w, and then setting the currents to 0. Okay. And that's it. And if you want connected, you act just on W. So this is what we know very well from field theory. So what is a conformal field theory? So definition. Conformal field theory is a theory where this quantum generating function, if you compute it not for the metric G, but if you make a local Wild transformation and you transform your current also, and because you see the field O transforms with some omega to the delta, the measure transforms with some power, and so on. So this J needs to transform with some power. The metric transforms with some power, so this guy needs to transform with some power, J of x. This generating function should be equal to omega for G mu nu and J of x. Okay. So this is our definition of a conformal field theory. It might look a bit formal. It will hopefully become very clear when we'll start considering a few examples. But you see what it tells you. It tells you that if you have your theory, you make some dilatation, you make some Wild transformation, some local Wild transformation, and the theory does not change. Okay? Now, an important next we can ask what kind of transformations X, so let me introduce the notion of conformal transformations. Please interrupt me if you have any questions. What kind of transformations X mu goes to X tilde mu? So conformal transformations are transformations X mu goes to X tilde mu such that the new line element, so conformal transformations in flat space, in RD, such that the new line element, which is just dx mu, just the Euclidean line element, is equal to some omega square of x dx mu dx mu. So they are transformations. X mu goes to X tilde mu of X, such that the metric for the new points differs by the original one by a Wild transformation. Okay. So these are conformal transformations. They are particularly important because if we have conformal transformations, then the definition of a CFT, it implies, it is not equivalent, it implies, it contains more information, but in particular it implies the following. So consider conformal transformations in RD. Let's see what they are in a minute. Okay, can you tell me one such transformation? Of course, for example, translations. Of course, translations doesn't change the metric, right? X goes to X plus constant, dx goes to dx, nothing happens. Dilatation. Okay, X goes to lambda X, this becomes just lambda squared times dx dx, so this is just a constant. Okay, so there are a few. We will work them out exactly what they are in a minute. But under these transformations, what this general definition implies is that correlation functions of our operators are given by omega to the minus delta 1 of x1, omega to the minus delta n of xn, times the correlation function before the conformal transformation. Okay? So this is something you can easily work out using the definition of what O is, using the fact that the generating function by definition of a CFT is invariant. It implies this relation. So sometimes people start with this relation as the definition of a CFT. Okay? Now this is a bit stronger, as we'll see in a minute, because this tells you that, okay, there are some transformations in flat space such that you do them and you are describing still flat space up to a conformal transformation, and then this is how correlation functions transform. Here I'm telling you, put your quantum field theory on any curved background, apply a wild transformation, and this is how the correlation functions transform. Okay, it's a bit stronger. For example, we will use the fact that it is a bit stronger to study, for example, conformal field theories on cylinders instead of flat space. Okay? So this will be important. Okay, very good. So now there are two things we can try to understand. So one thing I will show you maybe today or maybe tomorrow is that this is extremely powerful. I mean, if you know that your theory has this local scale invariance, and if you try to find correlation functions, and if you impose that correlation functions must obey this kind of equation, this is extremely constraining on your theory. It's extremely powerful. I mean, it's like Lorentz invariant. It tells you that, what does Lorentz or Poincare invariance tells you? It tells you that you must contract indices properly, right? It's already good. I mean, it tells you that you cannot start putting x mu, x mu, x mu with all the indices up and crazy stuff like this. You have to do things properly. It's good. It helps you. But this is even more powerful. So as we will see, this is extremely constraining. It basically fixes the 2 and the 3-point functions in your theory, which is extremely, extremely powerful. Okay, very good. But let's see what are conformal transformations, because there are not that many, actually. So we can easily list them. Yeah. Yeah. Yes.
So I don't know exactly how to say the question, but it's, so basically we're changing, we have a symmetry in our coordinates, and that fixes the transformation of G. Okay. Basically, we don't allow phi to change, for example. We don't allow transformation in phi independently of the coordinates.
So, I mean, this is the definition. So, is this definition clear or not? Okay. So, when it comes to using it, you can maybe ask me again. I mean, I know people are typically always confused. You always do X, do I change field, do I change just coordinates, and it leads to a huge confusion. So, I try to be, I mean, this definition I thought was unambiguously. It tells you that you have some function. It depends on the metric, on the currents. You evaluate it on these guys, you get the same result. So let's see in a minute what it implies for correlation functions and how exactly we think about it. I think it will be very clear. Yes?
Do you use the conformal transformations as moving your points around in your space-time and changing your length elements, or do you view it as changing the metric?
It's equivalent. It's the usual story between active and passive transformations. You can, depends how you want to think about it.
Okay.
Right? I mean, you can think that you have your space and you put the points at a bigger distance, or you can say that no, the points at the same distance, but now I consider a metric that measures different distances in different units, and then in practice it's the same as having moved them.
So do your tangent vectors change?
No, sure. I mean, when I do x to x tilde, vectors and tensors change accordingly. So this dx mu, you obtain it. I mean, you compute it by the. I mean, as usual, it's derivative dx tilde dx mu and so on. You change tensors and so on accordingly. Yes.
So does the conformal transformation? So it looks. It seems that the conformal transformation is just like the transformation on the metric. Is it the only?
A conformal transformation? No. So let's list what are the conformal transformations. Okay? So let's see what are the conformal transformations in dimensions greater than 2. There are only 4. There are translations. That just shift x mu goes to x mu plus some epsilon mu. there are rotations. There are dilatations. Let me write this one. It's maybe not trivial. X mu goes to lambda x mu. So it's easy to see that all these transformations leave all the transformations leave the these first two leave the metric invariant, and this one changes the metric by a dilatation. Yeah? And there's one more, which is called K mu, which is called special conformal transformation. That I will explain in a minute, but that infinitesimally, so now that I'm just going to write infinitesimally, x mu goes to x mu plus some infinitesimal parameter b mu x squared minus 2 x mu b dot x. Okay? So it looks, this one looks very, very strange. You probably do not recognize anything like this. Some kind of quadratic sheet. Of course, if you already studied a bit of CFT, of course you do, but otherwise you don't recognize. Is it fair? This looks a bit weird. Who is familiar with this transformation? Who played with this before? One? Someone else? Okay, so this one is a bit new. So let's discuss it a bit, but let me first just make some obvious comments. So these guys here are nothing but the usual Poincare group. This guy is a dilatation, so for which this omega of x is just equal to a constant lambda. Okay. So we see that we have indeed Poincare plus some other stuff. Now, what is this special conformal transformation? It's actually very simple to understand it. This special conformal transformation, so this is in the infinitesimal form. We will write it in its finite form now. Conformal transformation is something simple. You can think of it as you start doing an inversion. So this I is an inversion. What is an inversion? An inversion is a transformation that flips x mu into 1 over x mu, but of course how to write this properly? It is x mu over x squared. After an inversion, you translate, and after translating, you invert back. Okay? So you do an inversion on your space-time, you translate a bit, and you inverse back. Okay? So if you do it by a small amount, it's something that doesn't do much to your point. But if you do it by a big amount, it's some kind of a funny transformation. Okay? So under inversion, let's just see why this transformation is indeed a transformation that for which this is true. Okay? So what happens under an inversion? Under an inversion, it's easy to see, if this is your x tilde mu, that dx tilde mu dx tilde mu is equal to dx mu over x to the 4, or over x squared. So your omega of x is just 1 over x squared. So it's a dilatation, but the amount by which locally it acts like a dilatation where this is the weight. Okay. So this is omega of x. Of course, for p, omega is equal to 1. So you can see that in total you have some shift because of this omega, then you translate to another point, and then you have another shift by omega at the shifted point. So in total it is indeed a transformation that preserves the metric of that form. So let's see explicitly what this guy is. So what is it in its finite form? First of all, is it clear that it's a conformal transformation? Because it's a sequence of operations that do respect this property. So what is it? So we start with some point x mu and map it to x mu plus b mu. Then we invert it. No, sorry. First we invert it. So it goes to x mu over x squared. Then we translate it. So it goes to x mu over x squared plus some b mu. and then we invert it again. So it goes to x mu over x squared plus b mu divided by its square. Okay? And now if you just do a small, you just compute this square, you get x mu plus b mu divided by 1 plus 2b dot x plus x squared. Okay, just a question of multiplying and dividing by x squared and computing the square, which, when b is small, infinitesimally, sorry, here I wrote something wrong, b squared. When b is very small, b squared is you can ignore, and then when you expand this term out, gives this infinitesimal transformation that I wrote here before. Okay? Now, one thing that this was about d bigger than 2, let me put here in a box, that in d equals 2, things are much more powerful, because in d equals 2, if you work with some coordinates z and z bar, then z going to any f of z is a conformal transformation. Holomorphic maps preserve angles and so on. Okay? So this is something that, this is how Escher did his pictures. He took some picture and then he applied a conformal map, and then he got these funny pictures where someone is looking at some picture, then the picture contains the someone and so on. These kind of funny pictures are nothing but a conformal transformation applied to something. So maps, functions, x squared, sine of x, cosine of x, any transformation is a conformal transformation. So it's an infinitely dimensional symmetry. Here, it's easy to see, and you can see in any book, and it's not something conceptually very hard, that these are the only ones. So this is finite dimensional group, and those transformations are the only transformations there are. Now, okay. Any question? Yes.
So is inversion alone a conformal transformation?
Very good. So inversion. But because that question connects to exactly what I'm about to say, let me see first if there is another question. Are there other questions? This is something kind of important. So please ask if there is something unclear. Is it clear? Is it okay? Very good. Now inversion. Inversion, no. Inversion by itself, typically we don't count it as being a transformation, just because it is not something smoothly connected to the identity. So it is not something that you can indeed get in a smooth way by starting from the identity and getting there. So typically the inversion, you exclude it. For example, you can have some CFT that is kind of chiral. You can have some theory which is scale invariance, but if you see it in a mirror, you recognize that it's not the same theory. Inversion is something that flips its chirality, right? I mean, if something is rotating in one direction, you can easily imagine. I mean, inversion is like a reflection with respect to a spherical mirror. So it would indeed be bad if theories were chiral. So inversion is not part of the conformal group. But in practice, in real life, in practice, it is, as I'm now going to argue, if you have inversion, more or less, you are guaranteed to have everything else. Okay? So your theory, by a conformal theory, is a theory that admits these generators as symmetries. But I'm going to show that if you have Poincaré and inversion, automatically you get the last two. So Poincaré plus inversion implies that you have a conformal theory. So the real new guy is this inversion. This is the real special guy. Now the opposite is not true, but in practice it is. I mean, for scalar theories, for example, it is true. But more generically, it is not. Okay? Okay, so let's see why this is true. Okay, so this is a statement. Okay, so now let's see why. Well, the first observation we make is that if we have inversion plus translations, of course, we get K. Right? Because by definition, K, if you know how to make an inversion, P, and inversion gives K. Is it clear? Now, all I have to show you is that if you have inversion plus these two guys, you can also get D. You can also get dilatation. Okay? So if you have inversion plus these two guys, you can already get K. Can you also get D? Are dilatations an automatic consequence? Okay. So what about D? Well, just to practice a bit, let's work out some commutator between, say, K mu and P mu. I encourage you to compute the other commutators. It's kind of a useful exercise. But let's compute this one to see what kind of algebra is the conformal group. So what kind of algebra are we dealing with? Well, let's compute it. So what is this? So what is K mu? K mu is the generator. Let's compute it by using the action on points. So it generates this infinitesimal transformation. So what is it as a generator? Well, we read it immediately from there. It's x squared dx mu, right? So from the first term, minus 2x mu d, sorry, 1 second, x mu x alpha d dx alpha. Okay? Is it clear? This generator, if you contract with b mu and act on functions of position, generates that translation there. Is it clear? And p, what is p? It's d dx nu. Okay. And if we are doing it, let's do it properly. If we know that p, even though at least I always forget there is an I, it's I d dx, right? Because e to the ipx is what generates translations. It's not e to the p. So let's do it properly. Let's put an I and an I here. If we are doing Euclidean, that's why. If we are doing things properly, we should do it. Very good. Okay, but let's immediately remove the i's by just putting a minus. And now let's do it the way we would. Let's put it here I squared. And now let's ignore the i's. Okay, so now what happens? So you can imagine you have some test function. So this derivative, it can act on this x squared, or it can act on this x, or it can act on this x. Is it clear? So you get I squared. This guy acting here gives nothing, and then when you have minus this guy acting here, there is some term that survives when the derivative acts on the x. Because this is the second term, there is a minus. And now we just acted the derivative on the x squared and on those terms. So on the x squared, it gives 2x nu times d dx mu minus, if it acts here, it gives 2 some metric eta mu nu. It can be Euclid, it can be the signature you like the most. X alpha d dx alpha. And if it acts here, it gives minus 2 x mu d dx nu. And that's it. Now, what do we see? We see that these two guys, the first and the last one, what do? They do x mu dx nu and x nu dx mu. What is this? Just a rotation, right? So it's just a rotation. So if you have, say, so this is just a generator m mu nu. Okay, so this is the generator m mu nu. What is this one? What translates a quantity by x dx? Someone, x dx. Exactly. So this is exactly a dilation. So if we work it out carefully with all factors of I, we get that this is equal, if I did it correctly, to I eta mu nu dilatation plus 2I m mu nu. Okay. So we conclude that indeed, if you have inversion, you get K immediately. But if you have K, you can commute with P and generate dilatation. So if you have inversions, automatically you get it implies automatically that you have all the symmetries. Maybe I write here. Can I write here? Can you see if I write here? Is it okay? So in practice, it's very useful to have in mind that if we have Poincaré plus, so if you have Poincaré is trivial. Just indices are okay. And then we have the following. If you compute correlation function of your operator, and you do it of x mu 1 over x1 square on x n mu over x n square, you invert, you consider the points at the inversion, this should be equal to x1 square to the delta 1, xn square to the delta n, times just the correlation function of the operators O1 at your original points, x1 mu, On of x and mu. Then this implies, if this is true, we have a CFT. Okay? Of course, there might be cases where this is not sufficient, but if this works, it's not necessary, but if it works, it is sufficient. Okay? So let me end by writing an example where this is true. Okay? Let's see an example of a correlation function that does transform as it should. Okay? So example. And what we will see tomorrow is that it could not have been otherwise. It ought to be, this form is not one example that works. It's the only form that is possible by conformal symmetry. Let's take two operators. Let's have them be the same, OX, OY. And the example I want to consider is that they are given by 1 over their distance to some power delta, and this delta is what we call the dimension. Okay? Let's see what happens to this example. Okay. Even though I said this is enough, okay? Even though I said it's enough, let's understand the first three. Even though we don't need to check this guy, if inversion works, let's still do it. So, translations, obvious, right? It only depends on the distance. So, of course, it is true that O of x plus a, O y plus a is equal to 1 to some power delta 1, 1 to some power delta 2, times the correlation function O of x, O of y. I'm putting minus because if you see the definition here, it claims that this is what we should check. Okay, but omega is 1 for dilatation, for translation. So indeed, this is true. For dilatations, we can ask O of lambda x. Oh, okay, let's first do rotations. Rotation. Lambda x, lambda y. This is just a finite rotation. Again, the rotation doesn't rescale anything, so you have 1 times your original correlation function. Dilatations. O of lambda times x. So this is a matrix, right? Is it clear, this notation? Just rotation. You have a vector, you rotate. O of lambda x, O of lambda y. What is this? If you put lambda and lambda, you get 1 over lambda to the power 2 delta times 1 over x minus y to the 2 delta, which is just lambda to the minus delta times lambda to the minus delta times the correlation function O of x, O of y. This is the first factor. This is this omega at the point x1 to the power minus delta 1. And this is omega at the point x2. x2 is y, of course, to the minus delta 2. And the operators are the same, so delta is the same. Is it clear? You could check special conformal, but let's check inversion, because inversion plus the first two actually imply the second two, so we could just check inversion to start with. So let's check inversion. So under inversion, x minus y, under some inversion, goes to, it's easy to see, it goes to x minus y. So you just invert every point and you compute. Okay, let's do it. It goes to x mu over x squared minus y mu over y squared. Sorry. I'm confused now. Okay. So x minus y squared goes to this square, which is equal to x minus y squared divided by x squared y squared. Okay, just let me see. Is it true? Yeah, it's true, right? X squared. Yeah. Okay, if it's not true, tomorrow I can correct, but I think it's true. So what you check easily, therefore, is that because you have this, what happens is that your correlation function, x minus y squared to the power delta, under inversion, so correlation function at your point x mu over x squared, at y mu over y squared, okay, it's equal to, you replace it by this, so you have x squared y squared divided by x minus y squared, everything to the power delta, which is nothing but x squared to the power delta, y squared to the power delta, times the original correlation function at x and y. Okay. And this was indeed exactly, this is indeed exactly what we said should happen. Okay? Very good. So now what you are asked to do is the following. So what you will be asked to do in this afternoon is the following. So you are given, first of all the generators of the conformal algebra. So all the algebra relations of the generators. So K mu with P mu gives D, and you have a list of all the generators, okay? So you can just take all the generators. And then the question, one obvious question is, what is this algebra? Do I know this algebra? Is this algebra somehow familiar? I mean, is it SU2? Of course it's not SU2. You have more than 3 generators. But is it something that I know? And indeed, it turns out that conformal algebra in D dimensions is the same as the Lorentz algebra in D plus 2 dimensions. It's just a statement. So the conformal algebra is nothing but SO D plus 1, 1. Okay? The conformal algebra in 4 dimensions is the same as Lorentz in 6 dimensions. And more than that, you will play a bit with this algebra, work out these conformal transformations in this higher dimensional language, which is a very powerful and modern approach to conformal field theories, working in this so-called embedding formalism. And tomorrow we will start by some comments on this algebra and some comments on these conformal transformations. But I hope that this example explains clearly what is the recipe and what exactly we should do. I mean, does it address the questions that were asked? Is it clear what we are doing? Because sometimes people are a bit confused exactly what I shift, what I don't shift. I mean, is it clear, more or less? If not, please come and ask me. I mean, I hope everything is clear. So this is what a CFT is. These are conformal transformations. They effectively perform a wild transformation. Under this transformation, correlation functions should behave in a very special way. For example, under inversions, this is how they should behave, if inversion is a symmetry. And indeed, for a power behavior, indeed, it does transform in this way as we see now. Okay. Thank you.